All right, welcome, folks. I think we are going to get started. A couple of announcements as we begin. First of all, welcome to the 30th day of remote learning. Today's joke is a protest chant joke. So you might have heard the protest chant. It goes, "What do we want?" And then the people say what they want, whether it's nuclear demilitarization or an end to climate change. And then, when do we want it? Now. Um, so I have been to a pretty reasonable number of protests in my life, and I'm pretty familiar with this. So when I saw this joke, I was like, "That's really sweet," and I wanted to share it with you. And then the Black Lives Matters protest started up, and I didn't feel like it was an appropriate time to be joking about protest because what was happening was so serious. Uh, so hopefully now is a bit more of an appropriate time. It's certainly not a joke that's in any way connected to those things. I just didn't want to joke about protest at all at that time. So here is the protest chant. What do we want? Airplane noises. When do we want them? Meow. So hopefully you enjoyed that. This is our last lesson for the advanced functions course. We were going to be talking about composition of functions. And on Friday, if you would like to join at 1 p.m., so not our usual 11 a.m., but at 1 p.m., my grade 9 classes persuaded me that I should live stream myself playing League of Legends. So I will live stream on Twitch on Friday at 1 p.m. I am not good at League of Legends and don't have very much experience with it. So if you enjoy watching League of Legends fails, please join the stream. There will be many. All right. So let's jump right over into the math. So there are two handouts today, a regular one and the homework handout in the classroom. We'll be working through the regular handout. The homework handout lists at the top the questions to do. So please don't just do the whole handout. It's quite long, but instead take a look at the recommended questions up there. Okay, so today we are talking about composition of functions. In theoretical mathematics, composition of functions is one of the most important tools and a very useful topic. Um, and the reason is that the way it's kind of hard to explain this without going into some more in-depth mathematics. So I'll maybe say it like this. We've looked at functions that go from the real number line as its domain to the real number line as its domain. And we've talked about how in certain cases, the domain is not the whole number line, it's just part of the number line, and the same thing for the range. So you might have wondered, like, why do we keep coming back to talking about domain and range when we don't actually do anything with that? But we learned about it in grade 9 for linear. We did it again in grade 10 for quadratics. We did it again in grade 11. We've done it again in grade 12. Why are we always talking about domain and range and we never do anything with it? Well, the reason is that the domain and range of a function are in some ways a way to describe mathematical objects. And so we can often take a mathematical object and turn it into a particular set that is a domain of a function. And then we can describe actions or transformations on that object as functions. And so when people are looking to analyze new mathematical objects or real world objects that they can correspond with a mathematical object because of similar properties, they often will use functions to describe the actions that can take place. So one example of this is a Rubik's Cube, which can be defined as a mathematical object called a group. Um, and then by looking at the different functions that can be applied to that group, the different manipulations that you can make with the Rubik's Cube can be fully described mathematically. And people have discovered different ways to solve Rubik's Cubes based on this type of analysis. So that's one sort of famous example, but this type of thing happens much more generally. And it's just a really crucial tool of mathematics. And so right now we've talked entirely about functions that go from real numbers to real numbers. But in first year university, you'll start talking about much more complicated sets and functions that go from those sets to other sets. And one of the things that we can do is, based on this idea of composition and inverses of functions, is that we can show that two sets that seem to be very different from each other are actually essentially the same set mathematically. We use a function called an isomorphism, which is a function that itself and its inverse have some very similar properties. And it lets us draw very wide and very powerful conclusions about what's going on with these functions and about the similarities between these two sets or these two objects. So just wanted to give you a hint of an idea of why this stuff is important. It also just lets you make some really cool looking graphs, and it lets you model some physical situations that would otherwise be really difficult to produce a good mathematical model for. So it has a lot of engineering applications as well, but it's just a really fundamental mathematical idea. So let's dive right in. Just going to check here, make sure we can see what's going on. Oh, and rotate. There we go. Focus. Nope. Focus. Oh, it does not want to focus today. There we go. All right. So if you look at the handout 4.17.h, it is entitled Composition of Functions, Inverse Functions. It says review, but we're not going to do this as a review. So you can think of a function as a little machine that takes an x value and turns it into a y value. So if I have the machine that turns 1 into 1, and it turns 2 into 4, and it turns 3 into 9, and it turns 4 into 16, you are probably getting a sense that this machine is the function y equals x squared, or if we write it with function notation, f of x equals x squared. And that is certainly a machine that is consistent with this pattern. So the idea of composition of functions is that we take two functions and we apply them as this machine that takes an x and gives you a y. And then the second function takes this y value and gives you another value. So the example that we start with here is f of x equals x squared, not plus, minus 3x plus 2. And g of x equals 2x plus 1. And the first example that we're given is f composed with g of x. So this little empty circle here, it's not a multiplication symbol. It's not like the dot for multiplication. It's a different operation. It is composition, and it's an operation that only works on functions. You can't compose numbers. You can only compose functions. So we're going to compose the functions f and g. And I guess maybe I shouldn't say you can't compose numbers. You could consider each number as a constant function and compose it, but it's a really boring operation if you do that. Okay, so what does f composed with g mean? Well, it means that if I take an x value like 1 and I apply f to it, so if I put 1 in here, into the function f, I get 1 squared minus 3 times 1 plus 2, and that works out to 0. And then I am going to further compose g onto that. So, and I will get the final value f of g of x. So f composed with g of x. So I'm going to take 0, which is the result of f, and I actually realized I'm doing this backwards. So my apologies. F composed with g of x, we actually need to apply g first and then f. So let me catch that. So g of 1, 2 times 1 is 1, plus 1 more is 3. And then if we put 3 into f, we get 3 squared, which is 9, minus 3 times 3, which is also 9. So 9 minus 9 is 0, plus 2 gives us 2. So f composed with g at an x value of 1 is going to give us the answer of 2. So we apply g to 1 first, and then we apply f to the result of g of 1. So the number is going through the g function first, and then the result of that gets put through the f function, and the final result is equal to the composition's value. So go ahead and try this for 2. Can you figure out, using this process, what f of g of 2 is? And so I'll give you about 30 seconds to try that out. When you have an answer, please just go ahead and type it into the chat. Thank you, Caitlin. All right, so if you're finishing up your calculations, take a moment, do that. See if you got the same thing as Caitlin. And then we can look together here. So we know that g is applied first when we have f composed with g of x. That means we're going to do g of x, and then we're going to compose f onto the result. So g of x first, 2 times 2 is 4, plus 1 gives us 5. And if we substitute 5 in here, 5 squared is 25, minus 3 times 5 is subtracting 15. 25 minus 15 is 10. And 10 plus 2, I'm getting 12. Did I mess something up here? 2 times 2 is 4, plus 1 is 5. 5 squared is 25. 3 times 5 is 15. 25 minus 15 is 10. 10 plus 2 is 12. I think I'm getting 12 here, Caitlin. Do you see where we did something different? And if you do, I put 5 as 4. Yeah, okay, that makes a lot of sense then. Cool. Yeah, and that would give you 6. Okay, great. So this is the composition process. So as you can see, the calculation is multi-step, and you kind of just need to be careful about writing something from one step into the next place correctly. But other than that, the calculation is not like a tricky calculation. It's not like you have to think things through or figure something out in your head. You just have to go through and keep all of the steps in order and pass things appropriately. So that's the general idea of how it works. We are often interested in not only being able to calculate individual values, but in being able to determine an algebraic expression for the composed function. So what does f of g of x equal? Well, another way to think of it is it's literally f of g of x. So here it's maybe a little easier to see that we're going to do g of x first, and then whatever we get from that is going to be the input into f of x. But that also means that I can take f of x and I can say, well, that's f of g of x is going to be g of x all squared minus 3 times g of x plus 2. And that is, well, g of x is 2x plus 1. So it's going to be 2x plus 1 squared minus 3 times 2x plus 1 plus 2. So I've basically taken f of x, and anywhere there was an x, I've replaced it with g of x, which is 2x plus 1. So instead of x squared, I have 2x plus 1 squared. Instead of minus 3x, I have minus 3 times 2x plus 1. And then, of course, this is a polynomial. We can expand it. So 2x plus 1 all squared is going to be 4x squared plus 4x plus 1 minus 6x minus 3 plus 2. And if we collect our like terms, 4x squared, 4x minus 6x negative 2x plus 1 plus 2 is 3 minus 3 is 0. So we'll end up with 4x squared minus 2x. All right. And so you might look at that and you might be like, well, what's even the point of composing g and f of x when we could just write out this polynomial? And certainly, like if you have a nice direct way to get to this polynomial that doesn't involve two different functions, you're welcome to do that. But in many cases, each of the functions has its own meaning, and we're only able to get here by figuring out the two functions individually and then composing them together. But also, if your two functions aren't both polynomials, the combined function may not be easy to simplify to a polynomial, or may not be possible to simplify to a polynomial at all. And we'll see some examples of that. The reason that we're starting with polynomials is that they're a little bit easier to work with. And so it's a good place to start before we get to the trickier ones. Okay, so go ahead and see if you can calculate g composed with f of x, which is almost the same thing, but the order is different. And as you'll see, different ordering can create pretty significant difference in the result for composition. It's not like multiplication where the order doesn't matter. For composition, order matters a lot. So go ahead and see if you can do g composed with f of x. And once you get an answer, please type it into the chat. Thanks, Rumaisa. And Rumaisa, was that a 1 as like the whole function is always going to be 1? So no matter what x value I put in here, I get 1? Or did you get 1 for a specific x value? Okay, thanks, Rumaisa. All right, so let's take a look. If we want to get an algebraic representation of this function g of f of x, well, g of x is 2x plus 1. And we're going to replace the x with f of x, which is x squared minus 3x plus 2. So we have 2x plus 1, but the x is replaced with x squared minus 3x plus 2. And so now again, we can simplify this. 2 times x squared, 2 times negative 3x 2 times 2, and plus 1 is outside the brackets, so it doesn't get multiplied. And then finally, that's going to be 2x squared minus 6x plus 5. And so we can see if we sub in 1, which is what Rumaisa was talking about. She did it for x equals 1. So if we sub in 1 here, we're going to get 2 minus 6, which is negative 4, plus 5, which is positive 1, which is what she got. If we sub in 2, we'll get 2 squared is 4 times 2 is 8. 6 times 2 is 12. So 8 minus 12 is negative 4, plus 5. Again, we get 1. Will this always be 1? No, in fact, it won't. It happens that for 1 and 2, this quadratic has a value of 1. And that actually tells us that the vertex of this quadratic's x value is going to be 1.5, halfway between 1 and 2. But if you put in, for example, 10 squared is 100, 2 times 100 is 200, 6 times 10 is 60, 200 minus 60 is 140, plus 5 is 145. So if we sub in 10, for example, we won't get an answer of 1. We'll instead get an answer of 145. All right. So now we have an algebraic representation of g of f of x. Let me know what questions you have so far, or give me a 1 in chat if what we've done is making sense. Thanks, Caitlin. Thanks, Rumaisa. Okay. So I want to talk about one last thing before we move on to some slightly trickier ones, which is that we can compose a function with itself. So if we have g of x, then we can do 2x plus 1, but replace the x with g of x, which is, again, 2x plus 1. So here we've composed g of x with itself. And you can actually do this many times. And Rumaisa, you were asking me at the start of the semester some questions about the Mandelbrot set and about fractals. And you know that in fractals, we're iterating a function. Well, that's exactly what this composition is doing here. It's iterating the function g twice, but we can iterate it many more times than that. And in fractal research, that's one of the things that's often done. So here we go. 2 times 2x is 4x. 2 times 1 is 2. And then the 1 was outside the bracket, so it's not multiplied. So we end up with 4x plus 3. So composing g with itself gives us 4x plus 3. So then on the handout, it asks, calculate f of g of 2 in 2 different ways. All right, well, we've already done one of the ways. Up here, we calculated g of 2, and we got 5, and then we calculated f of 5, and we got 12. So that's one way to do it, is through this 2-step process. Calculate the inner piece of the composition first, and then the outer piece. The other way that we could do it, so that would be like saying f of g of 2, and then we calculate g of 2, and it's 5, and then we calculate f of 5, and we get 12. Or we could say f of g of x. Well, we calculated f of g of x up here. Oops, sorry. Let me make sure that's on the screen. F of g of x, and it is 4x squared minus 2x. And that means that f of g of 2 is going to be 4 times 2 squared minus 2 times 2. And that is going to be 4 times 4 is 16 minus 2 times 2 is 4. 16 minus 4 is 12. And so we're unsurprisingly going to get the same answer from both methods. But there's 2 different ways to do it. We can either calculate each piece individually and compose them. that way, or we can calculate the algebraic representation of the composition and then sub into that equation to get it. Okay. So let's keep taking a look here. In example 2, we have two functions, and their composite function is h of x, and we're not given the two individual functions. For questions like these, there turn out to be multiple different answers. So h of x equals square root x squared minus 4x. So we want to break this into two functions and compose them to make h of x. So one example would be to have f of x be the square root function, square root of x, and g of x be x squared minus 4x. And then if I compose them, f of g of x, well, f of x is square root of x, and we're going to replace the x with g of x. So I'm going to replace it with x squared minus 4x. And you can see that we do indeed get h of x. That's not the only option, though. We could also have said, well, let me flip it over here. Or we could do f of x equals x. G of x equals square root x squared plus 4x. I'm just going to check that I've got the sign right. Oh, minus 4x. All right. So if we did this composition, well, f of g of x would then be just x, but we're going to replace the x with g of x. So we would get x squared minus 4x. All right. So you can see there's more than one option. I didn't show you all of the possibilities here. There are more, but these give you some idea of how we can, or at least that there is more than one option. The other thing I want to point out here about composition is about what mathematicians call units. It's not like kilometers and meters and kiloliters and so on. In this case, when we say a unit, we mean the mathematical object for a particular operation that doesn't change anything. So unit for addition is 0. And that's because if you add 0 to anything, it doesn't change. Right? 5 plus 0 is still 5. Negative 37.8 plus 0 is still negative 37.8. So in addition, the unit is 0. But in multiplication, the unit is no longer 0. If you multiply 5 by 0, you don't get 5. You get 0. If you multiply negative 7 by 0, you don't get negative 7. Right? So in multiplication, the unit is 1. 5 times 1 is still 5. Negative 7 times 1 is still negative 7. So this is a unit. For composition of functions, the unit is x, or f of x equals x. The function x, if you compose it with any other function, you will just get the other function. And that's true regardless of which of the two spots in the composition it is. It can be on the inside or it can be on the outside. You're still always going to get the other function unchanged. Now, units also play a really important role in deciding opposites. So if I ask you for addition, what is the opposite of 7? The opposite is negative 7, and that's the addition opposite, right? And that is 7 and negative 7 are opposites for addition if and only if, when I add them, I get the unit. So 7 and negative 7, how do we know they're the opposites of each other? Well, if I add them, I get 0, and 0 is the unit for addition. So the unit is really tied to how we figure out whether two things are opposites or not, or to giving us a way to prove that two things are opposites. For multiplication, 7 and negative 7 aren't opposites. All right. So, and I guess maybe a little bit more about what we mean by opposites. If I take a number and I add 7 and then I add the opposite of 7, I should end up back at my original number. So if I do 5 plus 7, I get 12. 12 plus negative 7, I get 5, which is my original number. So that's what we mean when we say 7 and negative 7 are opposites. So that means that or opposites for addition. So that means that if I add 7 and I add negative 7 to the same number, I'm going to end up back where I started. They will have canceled each other out. And of course, you've been doing this for years and years with solving equations, right? Like at least 4 years now, you've been solving equations with this idea of opposites. So for multiplication, let's say we take 3. Well, the opposite under multiplication is not negative 3. Because if I take 5 and I multiply by 3, I get 15. If I multiply 15 by negative 3, I get negative 45. Well, that doesn't take me back to 5. So it hasn't undone the multiplication by 3. Instead, my opposite for multiplication is going to be 1 over the number. So if I take 5 and I multiply by 3, I get 15. If I take 15 and I multiply by a third, I get 5. 1/3 of 15 is 5. And so now I'm back where I started, which means for multiplication, 3 and 1/3 are opposites of each other. And you'll notice if we multiply 3 times a third, what do we get? We get 1, the unit under multiplication. So if we have two opposites under an operation and we do that operation to the opposites, we get the unit. And the same thing is going to be true of composition, and it's going to allow us to see what opposites are. So I'm trying to think of a good example here. I think probably the best one would be 3 to the x, or maybe we'll go with 4 to the x. So 4 to the x, we're looking for the opposite of 4 to the x under composition. Well, it's going to be log base 4 of x. And if we compose these, so if we do log base 4 of x, but we replace the x with 4 to the x, what do we get? Well, we get, according to our exponent rules for logarithms, the x comes down in front, so we get x log base 4 of 4, and log base 4 of 4 is 1. 1 times x is just x. So if we compose them, we get x. And if we compose them in the other direction, so 4 to the power of log base 4 of x, well, we know from logarithms, log base 4 of x is the exponent you need to put on 4 to get x. So if this is the exponent that we need to put on 4 to get x, and we put it on 4, we get x, right? That's the whole definition. Log base 4 of x is literally the right exponent to put on this 4 to make the answer x. So if we put it on this 4, we're going to get an answer of x. So you can see that we can show that these two are opposites under the composition operation because they give us the unit when we compose them with each other. They give us the x. All right. So that may seem like pretty different than the math that you've done before, and it is. It's definitely leading us down the path towards what I was talking about at the start of the lesson. Okay. So We're going to go to page 2 of the handout where it's talking about inverses. So that is what we were getting into here. The idea that two functions can be inverses of each other. And that means that if we take, say, the number 2, 4 to the power of 2 is 4 squared, so 16. And then if we take log base 4 of 16, we get 2. So if I do, let me show that, f of x equals 4 to the x, g of x equals log base 4 of x. If I do f composed with g of 2, well, that's going to be f of log base 4 of 2. Log base 4 of 2 is a half, so we're talking about f of half. And that means 4 to the power of a half, which is square root of 4, which is 2. So you can see here that if we have two inverses, f and g are inverses of each other under composition, and we compose them on the value 2, the answer we get is 2. Much like when we were composing two opposites in addition, they would get us back to where we started. We composed two opposites in multiplication, they got us back to where we started. We compose two functions that are opposite using composition, and it's going to take us from 2 back to 2 where we started. Okay, so inverses are the function. If you have one function, its inverse is the one that takes you back to where you started. That is its opposite, that cancels it out, is one way to think about it. And one way we can check that is that if we compose a function in its inverse, we should always get the unit, which is x. So how do we find the inverse of a function? Well, you already know how to do it because you talked about it in grade 11. So f of x equals 3x minus 12. How do we do this? Well, we switch the x and the y, and then we solve, or we isolate the new y. So I'm going to switch this to be x equals 3y minus 12. And then I'm going to simplify. So I'm going to add 12 to both sides. So I get x plus 12 equals 3y. Divide by 3, divide by 3. Y equals 1/3 x plus 4. So the inverse of y equals 3x minus 12 is y equals 1/3 x plus 4. All right. What questions do you have about that so far? And if you're feeling comfortable with it, you can just put a 1 in the chat. Thanks, Caitlin. Rumaisa asked, could we leave it as x plus 12 over 3, or does it have to be y equals x over 3 plus 4? You'd be welcome to leave it as x plus 12 over 3. These two are completely equivalent mathematically. Some teachers would be picky and say that this isn't simplified and that you need to fully simplify everything. It's true that this is not fully simplified, but they're mathematically the same object, and I personally doesn't make any difference to me which of these two you choose. In either case, you have the correct inverse. Okay, so let's take a quick look at an application to round things off here. So at the very bottom of the second page of the handout, there's an application on forest fires. So it says forest fires often spread in a roughly circular pattern. I don't think that's actually true, but we're going to pretend it's true. I think it's true if there's no wind and your forest is very uniform, but that's a pretty rare situation. So the second one says the area burned depends on the radius of the fire. The radius in turn may increase at a constant rate each day. Suppose that A of R equals pi r squared represents the area A of a fire as a function of its radius. And so that makes sense, right? So if the fire is circular, then its area, A of R, let me try that again. A of R is going to equal to pi r squared because that's circular area. And if the radius of the fire increases by 0.5 kilometer each day, so this is like the slowest burning fire ever. So the radius as a measure of time, it's only 500 meters, 0.5 kilometer per day. Then we have a formula for the area of the fire based on its radius. We have a formula for the radius of the fire based on how many days it's been burning. But what we really want is a formula for the area of the fire, not based on its radius, but based on how many days it's been burning. And the way we would get that is to take the area function composed with the radius function to get ourselves area as a function of time rather than as a function of radius. So let's simplify this out. So area is pi r squared, but we're going to replace the r with the radius function, which is 0.5 t. And then we're going to square that. So we end up with pi t squared. 0.5, that's a half. A half squared is a quarter. So we need all of this over 4. So now we have, using composition, a function that shows us the area in terms of the amount of time, the number of days the fire has been burning. And so if we want to find the area of the radius on the 6th day, we can do pi times 6 squared over 4 equals 9 pi. So that just gives you a bit of a sense of how we can put together two different pieces using composition of functions to get ourselves an answer. So that's going to be the end of our stream. Let me know what questions you have, or if you're feeling comfortable with it, if you can just put a 1 in chat and let me know that you're good with what we've talked about. Thanks, Caitlin. Thanks, Ramisa. Yes, you have a good summer break too. So as I mentioned at the start of the video, if anybody wants to join on Friday at 1 p.m., I'll be doing a stream on Twitch. I'll post the link in the classroom so you can just look at it as usual. But it's just going to be fun stuff, mostly watching me fail at video games. So this is our last lesson for the course. So thank you very much for a very interesting semester. It's been really nice to be able to do these live streams and to have some folks in asking questions. It really helps me to do a better job of explaining it. So I really appreciate those of you who've been able to attend the live streams, continuing to do that. And for those of you who haven't and are watching this in video at another time, I understand that it's been a really difficult and unusual semester and that you've been doing what you can. And so I appreciate you making the effort as your situation allows you to. If you do have any questions for me about anything in the course, feel free to send me an email. Next year, if you are off to post-secondary and you are taking math courses and there's stuff that's not making sense, feel free to send me an email. I'm happy to help you out as best I can with anything that follows on from this course. So do stay in touch and take good care. Have a great summer.